led me to specialize in quantum computing and large-scale data analytics. While writing my graduate thesis on rapidly sorting terabyte information sets, I struggled with the limited tools for directly visualizing and interacting with quantum systems. Existing simulators produced only static diagrams, lacking interfaces to make quantum principles intuitive. This spurred me to pioneer CoreAI's drag-and-drop environment for building circuits. At Corey's core is a robust simulator rigorously modeling quantum computations under the hood. But what sets it apart is the interactive workflow that gives form to quantum phenomena, like superpositions, entanglement, and interference. By placing gate operations along qubit wires, users create real-time visualizations, bringing the bizarre quantum realm into tangible reality. For example, dynamically rendered displays across the circuit architecture reveal probability amplitudes as rotating vectors, coherence information as matrix charts, and time-evolving algorithm steps as cascading state propagations. This interactivity supports rapid testing of systems otherwise too complex to efficiently analyze. My vision is for CoreAI to make quantum technology accessible for students, researchers, and professionals alike. The responsive interface allows exploring exotic physics principles, validating computational protocols, and prototyping practical applications from AI to finance. Whimsical science fiction comes to life as users perform teleportation of simulator-limited qubit states. Personally, I am dedicated to encouraging wider participation in this field, sponsoring community coding events to empower young girls in technology. I love blending my heritage's celebration of knowledge with the American pioneering spirit of bold innovation. With CoreAI, we stand at the cusp of a quantum productivity revolution, echoing visionaries like Feynman. Our classic notions of what is computing transform when the world itself becomes programmable at its most infinitesimal level. Join me on this journey to harness the immeasurable through mastering the minutiae. At the core of CoreAI are qubits and quantum gates. Qubits are represented by horizontal wires upon which quantum state vectors propagate. Users initialize qubits into states like 0, 1, 1, or superpositions via selection indicators on each wire. Quantum gates are taken from toolbox menus and placed sequentially on qubit pathways. Gates perform defined state transformations. For example, the Hadamard gate puts qubits into equal superpositions, while CNOT induces entanglement through conditional operations. Multi-qubit gates enable efficient combination manipulations. Users can even customize gate matrices and rotations. As gates interlink along wires into circuits, interactive displays visualize the non-intuitive internal workings. Block spheres map precise vector rotations. Probability charts enumerate exact outcome likelihoods for computational basis measurements. Amplitude displays decompose complex superpositions into component states. For correlated systems, dense matrices reveal complete coherence data across exponentially growing joint state spaces. Conditioning display outputs on other qubit results allows exploration of conditional evolution trajectories. This facilitates circuit optimization targeting enhanced probabilities for desired outcomes. Overall workflow is smooth and responsive. Users directly experience the dynamics of quantum systems rather than just static diagrams. Hello fellows, in this video I'm going to explain how to use the quantum circuit simulator. There's kind of a drag and drop quantum simulator that's very easy to use too. Open CoreAI, you go to the website and open that site. You'll end up looking at this, which is a menu where we can sign in or look at the source code, but probably we want to create a circuit, so right? Click this big edit circuit button, which will take us to this main screen. This part in the middle is the circuit, which was kind of boring right now. Each of these lines is one of the qubits. You can kind of make it a cube. So starting on the left and traveling to the right, hitting any operations that we put in, the way until they reach the outputs. Displays here which show us the final state of the system to add operations to. The circuit, you get them from the tool. Boxes above them below, for example, we can take this not gate click and hold and drag it into the circuit and let go. And we see that we've toggled the top wire from off on, and if we add another not gate, it will toggle back from on to off. You can add as many operations as you want to the circuit, including operation modifiers like controls, which condition operations and other wires. If you put something in the wrong place, you can just drag it to where it should be. And if you don't want an operation anymore, you can just drag it all the way out of the circuit. That'll remove it. You can also little click in order to remove gates, which is a lot faster. And if you want to make copies of existing gates, you can hold shift before dragging them. And that will make copies instead of removing the original. They may notice that whenever I'm removing an operation, around an extra wire shows up. That's actually how you add new qubits to the circuit. You just put an operation on that wire and it'll stick around. You can keep doing that again and again, all the way up to 16 qubits, which is the limit. Another thing you might have noticed while I was driving operations around, that the output displays actually update. In real time, you get feedback very quickly when you're using course A couple different types of output displays here. Others, these box ones, which tell you if the wire was measured. What's the chance that it would be on or off? I really need to emphasize the fact that this is gifts the wire was measured, because you can put these displays in the middle of the circuit, and putting them in the middle of circuit doesn't cause a measurement. In real life, you would need to do a measurement to get this kind of information, but in the simulator it can just be shown and there's no effect. There's no disturbing of the system. The next type of display over here, you're cutting circle displays, and they show the state of a qubit as a point on what's called a block sphere. And I don't really want to talk too much about the block sphere. You can look it up on Wikipedia if you want more information about it. The main thing you realize is that it shows more detail than these probability displays. For example, I can prepare two states that both have a 50% chance of being on or off. So you can see on those spheres, one is pointing to the left and the other is pointing to the right. These states are just as different as on and off, which are up and down, respectively. The last kind of output display is the most detailed of all and actually breaks down a superposition into individual amplitudes, which can matter. And the best way to show that is by setting up an entangled state like this and then using one of these dynamic operations, which are constantly changing. What they're doing by a little bit in order to create these nice animated effects. And what you can see is that the components of the superposition are changing quite a lot and quite noticeably. But if you look at the block sphere displays or the chance displays, you don't see anything abdomen. That's because they can't see these kinds of details when stuff is entangled. I will show you wanted to details about what these numbers mean and how to make sense of them. But if I get sidetracked into explaining quantum computation in general, this video would never. And so instead, I'm just going to leave some recommendations at the end of this video for other videos that you can watch, which do exploring the details. And I'm going to keep focusing on what exactly can QREI do so instead of talking about amplitudes. Let's talk about how do you say the circuit actually is really easy every time. Change is made to the circuit, the address, and the address bar changes to match. So if you bookmarked page, you're actually bookmarking the current circuit, not just query. So just make a bookmark and you saved circuit. You can also use this export menu in order to get a link that you can share with people or to download a copy of Coffee. We're on offline. That will open up to big circuits now. It looks like there is an awful lot of content left to cover. There's a lot of games toolboxes. But really, if you understand what it means to rotate a cube around the blocks here, which I know I haven't explained, but it's something that you can find out online. Club I Washington videos I recommend afterwards. You understand half of them already. These quality X, Y, and Z gates just rotate by 180 degrees around the X-axis, Y-axis. The Z-axis and these square roots of those gates were paid by 90 degrees. And then there's the 4th roots from the 8th roots and the 15th roots. And these continuous versions, your game U, can alter the interest and rotation. Around the blocks here, there's also Common operations that are well known, like to quantum Fourier transform or arithmetic of the rhythm tickets, are split into two pieces, which is kind of interesting as you move them around. Independently, there's also measurement, of course, but measurement is really a boring operation. All it really does is snaps tape to the z-axis on the block sphere. There's post-selection operations. These are kind of interesting. What it means to post-select is you do the experiment again and again and again. So whenever you don't get the answer you want, you try again. So here I'm inserting, if this wire isn't off, try again. So if I put system into a state where the wire 50% off the trip that on, this core collection will fail half of the time, but when it does succeed, the wire will be off. Now, lastly, if the operation you want isn't available, then you can link it with this make gate menu. So there's three ways to make a custom operation. You can define a rotation around the block sphere, or you can directly specify the proficient of the matrix. This entry is actually very forgiving in terms of what it accepts. It will automatically fix the fact that the matrix in image Aries for you, you can turn that off, although I wouldn't recommend it because you will get a junk operation that does things that don't make any sense. And often you can do is you can make an operation from the circuit itself, and this is useful when you want to avoid making the same thing again and again and again. Once you decided what gate you want to make, you get the appropriate create button and the gate will show up in the bottom, right? And the custom gate section, and you can drag it out of the circuit at this point. All the basics of using Curie, you know how to edit circuits, you can put displays in the middle in order to see what's going on. You save circuits by bookmarking them, and that you can make custom gates. What's left is kind of really the hard part, the basic quantum computing dollars to understand what you're doing, and also something that you want to do in the first place. Like, what circuit do you want to make? I can't really help with that, but I can help with the base of quantum computing knowledge by linking to other videos. I'll try to organize these from the most approachable to the most be useful. My first recommendation is that you watch the video Quantum Computers animated by PhD Comics. It's just a really relaxing video to watch. The next recommendation that I have is Curse Collapse Video Cross Computers Explain Limits of Human Technology. They managed to pack an absurd amount of information into 7 minutes after that. There's the mathematics of quantum computers by easing technologies. This kind of first video that will actually show any map at all. Next up, there's you. Don't know how quantum computers work by Frame of Essence. He actually goes over a circuit task which you can try out in court. And lastly, and by far the most useful, is the video lectures Quantum Computing for the Fellows. This style of videos where you learn as much as you would in a standard textbook for quantum computing and explains to you how quantum computing works.